going to talk in this video about Markov decision processes, but for that we need to identify and define several of our terminologies and get an intuition. So let's talk a little bit about decisions, right? So a decision can consist of two parts, the analysis and the making of the decision. So in the analysis, you present all possibilities, all possible actions. And in the decision making, you usually choose the best course of action. That's the basics of a decision. Now, it's not all that simple because we have another thing that influences our decision, which is the utility that we will get out of those decisions. So for example, when you pay more for a product, right, any product, is that a proxy of utility, like you're going to buy the best thing because it gives you more utility? Or you're going to buy the best thing because it gives you more happiness, or you can be cooler, right? So paying more for a product or proxy can influence utility, right? So the utility is not set. It's not a set concept. Now, for example, if someone in the street stops you and says, the first time says, I'm going to give you 100 chance of $300,000. So I'll give you $300,000, 100%, or I can give you $400,000, but with an 80% chance. What would be your decision? Right? Probably go with this. Although the expected value of this is more, you can see it here. The expected value of picking the second choice might give you more money, right? However, probably most people will pick this one because $300,000 is a lot of money, and this is a 100% chance. Now, another case, what happens if the person on the street says, hey, there's a 25% chance that you will make $300 or a 20% chance that you'll make $400? Perhaps in here, we're not too bad because both chances are slim. So maybe we'll just take the $400,000 because maybe we would have never won the $300,000 anyways, right? And that can also be seen with the expected value. So for example, 0.25 times 300 is 75. Now, 20% of 400 is 80. So for $5, you can make either decision. It's the same amount of money you're going to make almost. The same expected money, right? It's the same expectation of winning that money. Now, so we need to understand also the value. In order to make good decisions, we need to understand the value of information because that's going to tell us how much utility, how much value does that information have, right? We have to understand that versus a concept called likelihood. So for example, a test for cancer with small chance you might have it, that is talking about a likelihood, right? So when we look at utilities, we have to see why is it that we want, what is it that we want to get? What would maximize my happiness, my value, anything, right? But as we can see with these examples, it's not fair and square. We need information, more information to take these decisions. So let's talk a little bit about a scenario. Sorry about the slide swapping. Let's talk a little bit about a scenario. Let's say we have a robot. This is a canonical example. You will find this in many videos as well, and it comes from Russell and Norvik's AI book. Now, imagine you have a game, right? And the thing is, this is a sequential decision. So the robot starts here and needs to get out of the room here. It needs to get the reward. However, there's a wall in the middle, like there's obstacles, and if it takes the wrong path, it might end up in hell, which is -1. This is, you never want to do this at all, right? This is when you lose. Now let's define a few things here. Let's say that the robot moves wherever I tell it to move, right? Forward, backwards, right or left. But wherever it moves 80% of the chance is going to move there, and 10% of the chance is going to move sideways or to a place that I don't want to. This is because of an error, right? So robots are not perfect. There's a possibility they move to a place that I don't want to. So to exemplify this very, very bluntly, I'm just going to say there's an 80% chance that's going to go where I tell it to go, and a 1% chance that it's going to go sideways. Okay? There's no chance that it's going to go backwards. All right. And the robot, let's say it cannot move backwards. Now, we need to determine the transition model of this environment. The intended outcome will occur with probability 0.8, which is what I told you, right? And with probability 0.2, the agent's going to go sideways, right? So 20% probabilities, 10% on one side, 10% on the other side. A collision with a wall results in no movement, right? We talked about the terminals, +1 and -1 as the reward and punishment. And then here's something really important. All the remaining states here have a reward of -0.04. Now, what does a negative reward mean? A negative reward means that the more you travel in these things, you're going to get punished, because a negative reward is thought of as a punishment. So one can assume, for example, the more it goes around without getting to the exit, maybe the wheels get, can get a flat, maybe the fuel, whatever it is, it starts to diminish. There are many reasons to say why staying in the grid, or every movement in the grid, has a cost associated to it. Or oil wasted, who knows? Now, let's look at more terminology here. We saw a little scenario where the decision that we need to make, the scenario is no matter where we are, whether we want to move up, down, we have to make a decision, right? Those are the decisions. This is the information that I have. So like the components of a Markov decision process now are the robot or the agent that wants to leave the grid in this case, wants to get at the maximum output. Let's say for our purposes, each cell is a state of the robot, okay? And at each state, the robot can follow an action, go up, go down, go up, go left, go right. For each state and action, there is a transition model, denoted T or P. It's the probability of getting to a new state S prime, given that I was in state S and I executed action A, okay? And then for each state and action, there's also a reward function. So what's the reward of going to state S prime with action A coming from state S, right? Now, in many problems, you will see that the rewards are the same no matter what states you go to, and that's noted as R of S. This is the reward for every state that is not specified uniquely. Now, in the Markov decision process, what does the solution look like? So we have all the variables of the problem, but what would be the solution? How do we compute the solution, right? Well, first of all, let's look at what a solution to a Markov decision process might be. A Markov decision process specifies that the agent should, what the agent should do in any given state. So I put the robot in any one of those cells, and the Markov decision processes knows where to go next. Where to go next is called a policy. And then what happens is that the process of Markov decision process, the algorithms, will give me policies for each one of the squares in the grid. So no matter where my robot lands, there's a policy of where to go from that state. Now, of course, the policies can be many. Move up, move sideways, right? But what we want to do is we want to find the maximum or the optimal policy, which we know as P asterisk. And it's measured by the highest expected utility. So I will create policies of where the robot should move based on estimating my utility of that robot moving that way. Okay? So let's look at a little problem with the optimal policies. So given the optimal policy, right? Given the optimal policy, this is a result of a Markov decision process. We're going to see how to compute it later. But given maximum policies, right? The agent determines that is in a given state S, and then the agent takes the action given by the policy from state S. For example, if the reward in here is -0.04 for all of the states except for these two, right? And this because it's a wall. But so if the reward is negative 0.04, a Markov decision process output would output something like this. These arrows are the policies. Where do you move? So you start here, right? You move up, up, and then to the right. But however, if the robot lands here, for example, we want to move around here and get to the one. We don't want to go straight. From here, we don't want to go straight. And then if we're here, we definitely don't want to go straight because there's punishment, right? However, we have nowhere else to go. So we go here, and there's a 10% chance that we might end up in hell here, right? So this is risky. It's risky to put the robot here with this punishment, right? It's risky because it might deviate, right? It might go to the -1. But this is what the policies are for each one of the cells if the reward is negative 0.04. Now, just to give you an idea, the same problem with different rewards, which means we also might have risk, is this one, for example. If the R of S is less than 1.6284, right? Or, I mean, not a lot less, but less than 1.6284, the robot will try to go to hell right away, right? Because staying in the grid is too painful. Imagine the maximum reward is +1, and every time it moves is -1. So what the robot wants to do, the robot just wants to go, just want this pain to stop, right? If it's here, it's going to just go running to the -1. If it is here, then it might go to the +1. If it is here, it doesn't even want to move. It just goes to -1. Now, let's say that there's a reward that fluctuates between -0.4 and 0.08. Well, it'll try to do what it does if it starts here. If it starts here, for example, it'll try to go up. No matter that when you're in this cell, if you move up, there's a 10% chance you're going to fall to the -1, right? But the policy is not super lenient, so I really want to get out of here fast. I'll take the shortest route, although it might be the more risky one. Finally, two cases. When it's between 0 and 0.221, we get basically what we got the first time almost, where the robot wants to go on this path. No matter where it's at, for example, if it's here, it'll try to go back. Why? Because 80% of the time it's going to crash with the wall, but 10% of the time it's going to go out. It'll never go to the hell thing, right? So here the robot doesn't want to risk it at all. It's never pointing or hinting at getting to the -1. Always tries to go to the +1. Because the reward, the punishment is so little that we can afford to wait. Now, if the reward is greater than 0, it means that the robot can stay in any of these things and be happy. Rewards greater than 0 are positives, which means they're prizes to be won. So the robot will just stay in whatever position, except for here, it wants to go down, so there's no chance it's going to fall in the -1. If it's here, it's going to go here, so there's no chance that it'll fall in the -1. And if it's here, it'll escape, because staying in these cells for a long time, going this, at some point is going to surpass +1, right? Because these are rewards. So the robot really wants to stay. It's very comfortable in the grid. Now, if you have a finite number of steps, your optimal policy changes, right? So here, for example, we saw that this is an unlimited number of steps. This is just based on the rewards, right? However, if I tell you, okay, you have 6 steps to get to the reward, maybe you'll take different steps, right? Maybe your policy will change. Now, what would be the optimal policy if you had, say, for example, 3 steps in total? Well, it might just be try to get out very quickly, right? What if you had 2,340 steps? Well, you can relax your policies a little bit, right? It's not so urgent. Now, let's look at discounted rewards. So we're going to start getting our intuitions on how to compute these utilities, okay? So when you are offered, for example, a cookie now or 2 cookies in the future, what you are really assessing is what's the utility of eating the cookie right now or waiting. And if I wait, will those cookies have more flavor or not? Will they be more of a reward for me? Now, another way of discounting rewards is, for example, okay, if I say, pay me $30, okay, you owe me $30. But you know what? the person paying to me will say, okay, I'll pay it to you, but I'll pay you 5 now and 15 in a month, right? So what happens is that in a month I won't have my $20 because I probably spend the 5. I won't have like $20 in cash to spend. I'll have 5 now and 15 later. Can I afford it? That's my expected utility. What's the expected utility at the end? Probably just the 15 because I already spent the 5 for the 20. So the more time passes, the more my utilities change. Okay, my expected utility changes. So for example, the utility of a state at time t will be the utilities of all the states at time t, the utility of the system, I'm sorry. That is the same as the reward for the state plus some delay coefficient by the reward of the second one, and so on and so forth, with these numbers squaring and growing exponentially. Okay. Now, for infinite sequences with a gamma that's less than 0, we can think of the following. We can say that the utility at time t of all the states is the sum from t0 to infinity of this gamma to the t times the reward, okay? And that's going to be less than gamma to the t with the maximum reward or punishment, right? So this is the formula because we're delaying gratification. So each time I get a reward, because this multiplier here is less than 1, if I get all my rewards at time 1, I'm good, I win. But if I get rewards later on, I have to multiply it by something that's like, you know, my desired is not as much anymore. And then if you wait 3 years, my desire is not there at all. So this here is called the discounting rewards. This makes the reward be multiplied by a number that's less than 1, therefore a small reward. So so you can think of the traveling the grid, right? And we have a reward for S0, a reward for S1, but it's not such a reward anymore because I'm in S0 and this reward for S1 will be given to me in the future, and so on and so forth. Now, we saw the case for infinite sequences. Now let's look at the policies. The expected utility obtained by executing policy P starting in S is the following. It's what the formula we just saw. So at this utility, I will have this expected utility, which is basically the same summation. Look here. It's the same as this, right? Now, the optimal policy for a state S is the policy that maximizes, right, is the movement, is the action in this case, that maximizes the utility of that state over all possible policies. So if I have a policy in a state, right, the robot can move forward, right, or left. Those are going to be policies for state S. The optimal policy will be the one that actually gives me the state with the maximum utility, okay? That's the maximum policy. Now, in other words, the optimal policy is the argmax of the following. Is the argmax of the probability, transition probability, the probability that I arrive at a state S prime given that I was in state S and executed action A, for example, up, down, whatever, times the utility of S prime of this new state. That's going to be the optimal policy for that state. Now, the argmax of this. Now, here A is all possible actions, right? So we're going to iterate over the states here and then over all actions of state S, right? So we're going to do this summation here first with whatever action up. We're going to do for all S prime with A up. Then we're going to select the next action, which is right. We're going to do all the policy, all transitions from state S prime from S given A, right? So for example, if I want to, this probability is really simple in the sense that if I want to go up and this S prime is the state that's directly above me, then the probability of getting there is 80% by definition of the problem. We define that somewhere in here. right? We define it here. There's 80% chance of this going to in the right direction, and 1% chance that it's not. So again, let's look at here, right? So again, the optimal policy will be the one that the action that maximizes this probability. All right. Let's look at the expected utility here. This is called the Bellman equations. We're going to go into the Bellman equations very quickly, right? It's the utility is the reward of state S plus gamma times the policy, right? Plus gamma times the best policy, basically. In this case, it's not the best policy, but it's the value of the best policy with the state S prime. Now, I run this algorithm in a grid, and these are the values that I get for each one of these utilities. These are expected utilities. Now, with the reward being negative 0.04. How do I run this as an algorithm, though? Well, let's look at this. It's RS plus gamma times the maximum, the value of the maximum policy for state S prime. So let's look at it at work. So first, I can randomize these values. Let's say that these are randomized. I know that utility of 1,1 is negative 0.04 because that's all there is there, right? Now, if I go up, I need to compute the maximum of all the actions. So if the action is up, I have a 0.8 probability of going up times the utility of 1,2 because I'll end up in 1,2. Right? I'll end up here. Plus, there's a 1% chance that I will end up here because the robot can move sideways with 1%. And there's a 1% chance that I stay here because I try to go and there's a wall, right? So I stayed here. This will give us a number. Now, left. What happens if I choose left? The action is left. It's a 90% possibility that I'll stay here, because if I choose left, there's 90% chance that if I choose left here, I will bounce against the wall and I will stay here. 80% of the times I'll go there, plus 10% of the times I'll try to go down, but it doesn't go anywhere. So 90% of the times I'm going to stay here, right? 90% of the times plus the utility of 1,1. And 0.1% of the times that I go to 1,2. Right? So I'm here, I wanna go left. I'm sorry, 1,2 here. I wanna go left. I have 80% of a chance hitting that wall, 1% of a chance hitting that other wall, which means that 90% of the times I'm gonna stay in the same place, and 10% of a chance to go up or right. Now, if I choose down, it's a similar situation. If I choose down, I'm going to hit this wall. There's a percentage of times that I will hit this lateral wall, and there's a 10% chance that I will move to this space, which is basically what it says. There's 90% of staying in the same state plus 1% of going to the next state. And then if I go right, it's just like in the first one. There's an 80% of going to 2,1 here, but there's also a small percentage of going up and a small percentage of staying in the same place. So you compute these utilities, right? Utility of 1,2, for example, these values are here. Utility 1,2 is right there. Utility 2,1, I'm sorry, this is utility 2,1. Utility 1,2 is right here. So all the utilities are here, randomized, right, randomly. So you can compute what their utilities are. Now, this can also be applied in a graph terminology if that suits better, because it doesn't have to be a grid, right? But say, for example, this is a dialogue system in which providing the answer is what you want to do. And if you're talking with the person, there's some percentage that it will provide an answer right away, and that gives you a +2 reward. There's also a percentage of times that the action will be asked, right? The action of the agent will be asked for more information, and that's a reward of 0.03. So you stay with the agent, we're good. Now, with the agent, The agent can also ask to clarify to the person. The person can ask questions. The person can leave the chat. The person can keep asking questions here, right? And all of this has a reward and a transition probability here. Going to stop at rewards -1. You never want to be there. You also don't want to have the person clarify too much, because every time they ask you a question, it's a negative reward. So you can create like a little graph like this where states are not a grid, but there's something else. Again, and here is the same thing, right? So the Bellman formula. Now, because there are different rewards here, not just one reward, instead of RS, we do this notation. The reward of going to state S prime coming from state S with action A, right? Because every action here, every reward is different for every step. Now, we're gonna look at one algorithm only of how to solve this. There's basically 3 algorithms. There's one called value iteration, which is what we're gonna look at now. There's policy iteration, and there's using linear algebra. We're just gonna look at the value iteration in this video. The idea would be to start with arbitrary utility values as initial values, and then update them to make it locally consistent with the Bellman equations. So everywhere locally, if everywhere is locally consistent, that means that we will end up with a global optimality. So here's the algorithm. It's very simple. So you set the utility of all the states at time 0, because again, this is Markovian. So it's going to iterate over the states, right? Caring about the last probability that it computed. So we set the utility at time 0 of every state equals 0. So we're going to initialize all utilities to 0 for the first time. And then for a loop that's very long, or until utilities converge, we will do the following. For each state in S, right, I'm going to compute the utility of that state I plus 1. So in the next step, the utility will be the maximum of, and this is the Bellman equation. This T is the same as P, okay? So the probability of transition times the reward to going to that state plus gamma raised to the I of the state I, right? So if we're computing state number 2, utility number 2, this is gamma to the second. This is the equation. As you can see, it's recursive, because it's going to start asking us for the previous utility of a state, and we initialize all to 0. And as we go computing this for several iterations, these utilities are going to change. But because we're always computing the next utility, we already know the previous one, right? So it's a bit of dynamic programming right here. And recursiveness. So we depend on the previous value. Now, convergence. Well, convergence happens when the utility... Excuse me. So the utility of any system, right, will start adapting itself, and we will find values. Now, when this utility, the value of this utility is not too different from the value of I plus 2, for example, then we can say that the utilities have converged, okay? Now, at every given point in time, we're going to be selecting this probability, which becomes really important, because we can know what's the maximum utility. We know the value, but what we need is the action that maximizes that utility. We need the policy. So this equation, it's a recursive relation. It's a one step ahead, because I'm computing the next one, right? And U pi s are the expected discounted rewards in a policy starting in state S. So what I can do also, as I do these things, we will hold this one constant, and we look at the probability that resulted in the maximum in the maximum sum here, right? And that is what we're going to use as policies. So when you're programming this, you store the U's, and you'll store these probabilities too, okay? To see which one was the maximum. So you want the argmax of the probabilities that maximize the utility, okay? And that is value iteration. That's the basics of Markov decision process.